Hello everyone, welcome to the session on surface tension and viscosity. I am Rahul, Assistant Professor of Physics, GVPP, Government First Grade College, Hagari. In the previous session, we have discussed about viscosity, its meaning, definition, and we have also seen streamline and turbulent flow of liquids. In the session 6, we will discuss about determination of coefficient of viscosity by Poissulle's method. Let us begin. Determination of coefficient of viscosity by Poissulle's method. In the previous session, we have discussed about the coefficient of viscosity. It is defined as the tangential force acting on the unit area of a liquid moving with unit velocity. And the coefficient of viscosity is a very important property to know. It gives us information about how a liquid flows. To determine the coefficient of viscosity, we will use Poissulle's method. It was given by a French scientist called Poisulle. Consider a capillary tube of length L as shown in the figure like this. Okay, we have taken a capillary tube and let R be its radius. Now at the center of the tube, the layer which is flowing will have maximum velocity. This is because we have discussed in the previous class that the layer which is directly above the surface of the capillary tube will be at rest. Now the layer which is above will have some velocity. The layer which is further above, the velocity is increasing. So at the farthest away the velocity will be maximum. Now the capillary tube will have the other side also, there will be a surface, and the liquid molecules which are lying on the surface here will be at rest, and as we move away from the surface like this, the velocity of the layers is increasing. So the layer which is at the central axis of the capillary tube will have the maximum velocity, and as we move away from the central axis, the velocity goes on decreasing. Now let us consider two layers. Let first layer be at a distance x from the central axis like this. Okay, it is at a distance x from the central axis. And now consider second layer which is above the first layer, that is here. Let it is at the distance x plus dx from the central axis. We know that the tangential force acting on the opposite direction to the direction of flow is given by Newton's law of viscous force. Now for the layer at a distance x from the central axis like this, see, imagine it is a capillary tube, so the layer will be a circular one throughout the capillary tube. Okay, this in this circular the layer will be present, and this layer is at distance x. Now for this, the tangential force is given by F equals to minus theta A into dV by dx, where A is area of this cylindrical curve and dV by dx represents the velocity gradient. Now we know that for a curved surface of the cylinder, the area is given by 2 pi RH. Now for this layer, the layer that we have considered, for this layer, the R is nothing but it will be x, because it is at the distance x from the central axis. H is the length of the tube, which is L. So you get area of the layer that we have considered, which is 2 pi XL. Substituting this, we get F equals to minus theta 2 pi XL into dV by dx. Take this as equation 1. Now the force at the end of the tube, consider this is the end of the tube. Now the pressure difference or the force with which the liquid will come out of this depends on the pressure difference between these two. That force is given by P into pi x square, because pressure we know that it is force per unit area. So force will be pressure into pi x square, because x is this one's radius. and P represents the pressure difference between the two ends of the capillary tube, that is from this end, first end, and from this end and the second end, what is the pressure difference, that is given by P. Now for the liquid to be in a steady flow, these two forces, that is forces due to tangential one or viscous force, must be equal to the pressure difference between the two ends. When these two forces becomes equal, the fluid will be in steady flow. Therefore, equating equation 1 and 2, you get this much. Minus theta 2 pi xl into dv by dx equal to p into pi x square. X cancels here, pi get cancels. You are left with dv by dx equal to minus px by 2 neta L. Now consider dv only. dv equals to minus p by 2 neta L into x into dx. On integrating the above equation, we get integration of dv is v, which is the velocity, equal to minus p by 2 neta L into integration of x into dx, which is x square by 2. 2 into 2, you get 4 here. So velocity will be minus p x square by 4 neta L plus integration constant, let us take it as k. Now consider when x equals to r, that is the layer that we have considered is at the distance r from the central axis, which is nothing but the layer which is attached to the molecules of the capillary tube. Now we know that this layer doesn't move and it is at rest. So the velocity will be 0 when x is equal to r. That is, at the surface the velocity of the liquid is 0. Substituting these two values here, if you put x equals to r in this and v equals to 0 here, you get k value, that is k equal to p minus becomes plus when it moves to the other side, p r square by 4 neta L. Now we know the value of integration constant k. Substitute this, you will get the value of velocity v, which is minus p x square by 4 neta L plus, here k is replaced by p r square by 4 neta L. Adding, you take out the common p by 4 neta L and inside you are left with r square minus x square. Take this as equation 4. Now see here, equation 4 gives the velocity of the liquid layer at radius x from the center of the axis. Now to find out the volume of the liquid flowing per second between the layers, which is nothing but we call this as flow rate. The volume of the liquid flowing per second between the any two layers. Now two layers here we have considered is at a distance x and at a distance x plus dx. Now to do that, we must know the cross sectional area between the layers x and x plus dx and the velocity. We know the velocity v from equation 4 and the cross sectional area between the layers of x and x plus dx is given by 2 pi x into dx. So dv, which is the volume flowing through the layers between x and x plus dx. This volume is given by 2 pi x into dx into velocity. Now, if we integrate d between 0 to r, that is throughout the radius of the capillary tube, you get the total volume of the liquid flowing through the capillary tube. Now, before integrating, first substitute the value of v from equation 4. We get dv equals to 2 pi x into dx into p into r square minus x square divided by 4 neta L, where dv is the amount of volume flowing through the layers between x and x plus dx. Now to find out the rate flow of the liquid throughout the whole tube. For that, substitute, we have to integrate the dV. V equals to integration from 0 to r of dV, which is equals to integration 2 pi x into dx into p of r square minus x square divided by 4 neta L. Now here the variable will be x here, which is the layer distance that we have considered, and r is a fixed one. So multiply x inside the bracket here and take dx here, remaining terms outside. We get pi p divided by 2 neta L integration of 0 to r into r square into x here minus x square into again x, which is x cube into dx. So integrating, we get r square into integration of x is x square by 2, integration of x cube is x to the power 4 divided by 4. Substituting the limits 0 r, we get r square into r square, which is r to the power 4 divided by 2 minus, instead of x place r, so r to the power 4 by 4. We get the volume V equals to pi p divided by 2 neta L into r to the power 4 divided by 2 minus r to the power 4 divided by 4. On further simplification, we take difference of r to the power 4 by 2 minus r to the power 4 by 4. We get r to the power 4 by 4, which we gives us V equals to pi p r to the power 4 by 8 neta L. We are calculating for coefficient of viscosity, so take neta, which is equal to pi p r to the power 4 by 8 L V, where r is the radius of the capillary tube, L is the length of the capillary tube, P is the pressure difference between the two ends of the capillary tube, and by knowing the V, which is volume of liquid flowing through the capillary tube, we can easily calculate the neta, that is coefficient of viscosity for a given liquid. And that completes coefficient of viscosity through Poissulle's method. In the next session, we will discuss about coefficient of viscosity through the Stokes method. Thank you.